In the past few days with our notebooks, right, we have been working on building models, right? So the next step is once we have a model, we want to talk about how we can evaluate that classification model. We want to try to not just describe a model as like good or bad or like okay. These are more like qualitative descriptions. We want to start thinking about like how we can quantitatively measure the performance of our model. Instead of just saying something looks good, we can say like this model looks good because it has these metrics. All right, so let's start off with a little story. Let's say we're training a object detection model that will be able to detect dogs, right? So if we're doing this like we've been going through the camp, we might start off by collecting a few images of dogs. Say we have like these 3 images. Next, we would go about labeling them in label box, right? So maybe we say, okay, that's a dog, right? Maybe that's a dog too. We have like another dog there. And finally, we have like that dog, right? So we've labeled all of our images of dogs in label box, right? Then we download those from label box and we train our model, right? So we're going to train that model and then we have our model, voila, right? So now that we have our model, we want to see like, does this model actually work, right? And so maybe we get a picture of a dog and we test it out, right? We see now that we have this picture of a dog, let's test it. And then it finds the dog, right? But with this example here, what's wrong? What's wrong if we have this picture of a dog and we're detecting it? So the model has already seen this photo of the dog, right? If we go back to our images that we were using to train, right, we had this same exact photo. And so we told it exactly where the dog was in that photo. And then the model used that to kind of learn what to look for in a dog. So if we're using the exact same data to test that we use to train, this could cause issues, right? One of them could be it would reward overly complex models that like overfit the data, right? That could be one thing that happened. Like in this case, since it's already seen this dog, obviously it will be able to detect this dog. So to make sure our model is generalizable and it'll work for like all pictures of dogs, we might want to test it with images that it has not seen before, right? With that being said, we're going to transition into this idea of a train test split. This is a common paradigm in machine learning. Once you have like your labeled data set, you're going to want to split it into your training data and your testing data. That way, you'll be able to train your model using like the majority of the data. And then once you have a model that's been trained, you can test it using data that the model has never seen before. And this will give you a more accurate picture if your model is generalizable to out of sample data, right? In our example with the dogs, right, this might kind of translate into something like we trained on those 3 images of dogs, right? But then maybe we bring in a new picture of a dog that the model has never seen before as our testing data to make sure that the the model can detect like a dog, even if it's never seen it before, right? Because that would kind of be the test of like a nice generalizable AI, right? So to kind of take that from more of a specific example to like a general, we'll have our labeled data set, right? We're going to split it into our training data and our testing data. With our training data, we are going to, we might choose a learning model. Like, so for instance, we might choose something like a linear regression model or like a random forest classifier. We'll train that model using our training data, and then we'll get a trained model. Once we have this trained model, we can evaluate the model. So once we have the model that we've trained, right, we can kind of start to test it. Like, how good is this model? Like, does it work? Does it work with images we've never seen before? This paradigm is useful for its speed, simplicity, and flexibility. You can change the ratio for your training and your testing data, but some like common ratios are maybe something like 90% training, 10% testing, 80% training, 20% testing, maybe 70% training, 30% testing. These are all kind of reasonable, and the ratio that you choose might depend on your data. Perhaps like you may need more emphasis on creating a generalizable model. So if you really want to make sure it works with stuff that you haven't seen before, you might choose to make the testing data set a little bit larger. That way it's just testing more out of sample data. This is a little bit flexible. As I said, that's one of the perks of this paradigm. Commonly though, it's important that the training data set is larger than the testing data set if you want to train a model that's better, I would say. Next, we're going to discuss perhaps a potential problem that could come up if we're using just a single training testing split, like I described above here. So it's useful in a lot of ways, but what could be some drawbacks of it? One thing that could happen is perhaps we don't have enough data. So we would like to use as much data as possible for training. And luckily, when we're working with our projects in this camp, right, when we're using YOLO and we're collecting our images for our object detectors, right, the 1,000 images or so that we're collecting for each class is likely to be enough. But there will be some cases where maybe you're working on a project where you don't have enough data. Maybe it's not available, right? There's some examples of projects that you might do where data is really hard to come by. Perhaps you're doing something like in the medical field, and medical records can be really hard to get. So if the data is very scarce, it might be a problem to only use a single training test. Also, it could be the case where the training data is not general enough. Perhaps you found your data from just one online source, right? Maybe you found like a Kaggle data set. This actually happened to me in the last session, and we didn't have data that was generalizable enough. So it performed pretty well on that specific data set, but it wasn't generalizable at all. And one way we can fix this is we can use random sampling. And so I'm going to illustrate that a little bit here. So what this might look like is you could systematically create, let's say, n different training test splits and average the result together. So when I say n different test splits, we have the same labeled data set, right? And maybe we choose to randomly split in this first split. We'll say these 70% of the data are training and these 30% are testing. That'll be the first split. And then for the second split, we start with the labeled data set again, and we do just a different random split, right? So we're doing 70% training again and 30% testing, but the data that we have in the two sets, it's arranged differently than we did in the first split, right? And then we can do this n times, where you get to specify n, how many times you do it, right? Then once you have the results from all these different splits, you can average them together or choose the split that gave you the best result. And this will give you an even better estimate of out-of-sample performance. So it'll tell you better if your model is generalizable or not. I know this can be a tricky topic. So let's say I'm going to just use a small data set for like the sake of example, right? So maybe like our data set is numbers 1 through 10, right? And so maybe in this first split, we'll randomly assign the 10 numbers to either training or testing. So since we want 70% in the training, we'll say 70 or 7 of the 10 go in the training, right? So maybe we randomly say all the numbers except for 2, 5, and 8 will go in the training. And then the testing will be like the 2, 5, and 8, right? And then maybe in the second split, right, we do just a different 7 numbers here in the training and the other 3 in the testing, right? So it's just like you are partitioning your data in a different way in each split, but you're using the same set of data that you're partitioning. But obviously, like instead of just simple numbers, your data would likely be something like the images that you've collected, right? If you're doing like an object detection. So maybe you have 10 images. We're thinking of each of these like splits, right, as like an independent trial, right? So in this first split, this is the training data set and this is the testing data set. And then the second split, like down here on the second row, we're going to use the same data from the labeled data set, but we think of this trial as completely like separated from this other trial, right? So even if there's some overlap between maybe this testing data set and this training data set, that doesn't matter because we're mentally separating these, right? Just what matters is that we don't have the same data here in the training set and the testing set for the same split trial. So far we've only talked about a training set and a testing set. But oftentimes too, we are going to want to use another set called the validation data set. So instead of just having training and testing, we would have training, validation, and testing sets. As like a quick little activity / exploration for you guys, take about we'll say 3 minutes to go on Google and kind of try to find out what validation data sets are. And then I'll ask you guys what they are, and we'll have like a little discussion about what they are and why we use them. Take this moment to go try to figure out what they are, and then we'll talk about it together. So the validation set is going to be another set that we're going to use. It'll be about the same size as your testing data set, so it's going to be much smaller than the training data set. And it's going to be a sample of data used to provide an unbiased evaluation of a model fit. And so kind of how I like to think about it is kind of like you're studying and taking a exam. If you're preparing for an exam, right, the training phase might be you are like studying for the exam, right? And then the validation set, it might be used for you as like a practice exam, right? So it's still like maybe data that you haven't seen before while you were testing, right? But you're able to see like how well you're able to do on the exam, right? And then that way you can go back and study the things that you still need to like brush up on, right? And then once you have finished training, then you use your testing data set, right? And then that would be like your final exam, like the real deal test. You use the validation set while you're training, right? And this will help you kind of like tune your hyperparameters and make sure it'll give you like a measure of how well your model is doing like as it's training with data that it hasn't seen before. And then once it's finished training, then you just use your testing data set one time. When you're splitting your data, you'll have control over like what you make your ratio. So you can either like decrease your training data set if you're using a validation set, or you can decrease your testing data set, or you can like decrease them both a little bit. Some common ratios, and you'll see this later today, you're actually going to be splitting your label box data if you haven't already. But some common ratios would be maybe something like 80% training, 10% validation, 10% tests, 70% training, 15% validation, 15% tests. This will also be something that you'll get to see in action with our project. So next, we're going to talk about the emotion detector. What we're going to talk about is how did we evaluate our emotion detector? And one metric that we used to evaluate our emotion detector was accuracy. So accuracy would be the number of total correct prediction. In this case, we're calling it like total rights or total corrects over the total number of testing photos. So say we had 100 images and 83 of them were correctly predicted, then we would have an 83% accuracy. I would say accuracy is definitely an important measure, but it's not always the best way to evaluate our model, right? There could be times where we have really high accuracy and a really terrible model still. And we'll see an example of that. Accuracy is one good measure that we could use, but we're also wanting to consider other metrics to give us a more complete picture of whether or not a model is strong or not. Let's consider like this example to make this more concrete. We could have like a large class skew. So say we are building a classifier that will detect fraud cases, right? Let's suppose like most cases are not fraudulent, right? So fraud is not super common, but when it does happen, it's a big deal, right? So maybe for every 1,000 cases, right, only one of them is fraud. So if we were to just simply predict everything is not fraudulent, we could get nearly 100% accuracy, right? So if we had like 1,000 examples and only one of them was a case of fraud, we were to just predict everything as not fraudulent, we would have a really high accuracy, right? But this model is not really like useful for us in any way, right? It'll help us like make a correct prediction for most cases. The ones that really matter, it's not going to perform well on. Along that same idea, different classes of misclassification have different costs. If we're classifying fraud cases, one like false negative can cost you like an entire bank account, right? So like say you were unable to detect a fraud case and you said that something was not fraud when it actually was, that person who is being like a victim of fraud could lose like their entire bank account, right? So it would be like much worse in this case to predict a false negative than a false positive, where maybe like you say that fraud is happening when it really isn't. And maybe in that case, you might shut down their credit card or something, and they might be inconvenienced or kind of like upset, right? But that is not as bad as the false negative situation, right? Where we are costing them their entire bank account. This might be another image that you are familiar with if you've seen the emotion detector before, right? This is the confusion matrix for the emotion detector project. We're going to be making one of these for each of our projects as well. But let's take a look at this. Kind of how we would interpret this is we have some true labels, right? And we have the predicted labels. So up here, if the true label was happy, this means on the image, right, the actual label that we put in label box was happy, right? So if we were to look at this confusion matrix, it correctly, our model, this is the predicted label, right? Our model predicted happy 79% of the time when the actual label was happy, right? But we can see that maybe 8% of the time when it was happy, it made a mistake and predicted it as angry instead. Or maybe 10% of the time, it made no detection at all when it was happy. So when we're looking at the confusion matrix, these boxes along this diagonal line, right, where the true label matches up with the predicted label. So you see like here, the true label is happy and the predicted label is happy. Here, the true label is neutral and the predicted label is neutral. All of these boxes are going to be our correct predictions, right? And then the rest of the boxes will kind of tell us like what kind of errors we're making and with what frequency are we making those errors.
So basically, the confusion matrix shows the correlation between each matrix, between each features, right?
I'm not sure that's how I would explain it, because I would say these are the classes, not necessarily features. Okay. So like on this side of the matrix, right? Yeah. This is where we're going to have the true labels. So this is what is actually labeled in the picture, right? Because we labeled all of our data in label box. Mm-hmm. And then here on this axis, this will tell us what the predicted label was. So maybe if we're looking at, let's say, this box right here, what would, for these images that were predicted in this box, what was the actual label of those?
Neutral.
Yeah, and what did the model predict?
When they predicted it was sad.
Yeah, awesome. So that would be a mistake, right? Because it was actually one thing, but it predicted another. And we can say out of all of the neutral images, we made this kind of mistake where we predicted it as sad with 4% of the images. I would think about these not as much in terms of like correlation, but more in terms of maybe frequency. Here, if we're looking at a confusion matrix for just two classes, right? Our classes being either positive or negative, we would define our accuracy as the total number of right or correct predictions over the total sample. Our correct predictions, right, are going to be the true positives, where the actual class was positive and the predicted class was positive, right? And the true negatives, where the actual class was negative and the predicted class was negative. So the total correct would be the true positives plus the true negatives over the total sample, which would be all four quadrants. So let's go back to our fraudulent cases, right? So let's say we have 1,000 cases, right? And we are just going to predict negative, right, for all of them. So we're saying none of the cases are actually fraudulent, even though some of them are, right? If we look at the actual class, we do have 10 that are fraudulent, positive fraudulent, but we're just predicting all of them as, right? So in this case, what is the accuracy here?
Like 99%.
Yeah. So the accuracy would be 99%, right? Because we have 990 correct predictions over 1,000 total. So the accuracy here is going to be 99%. So the accuracy might be like deceivingly high, right? Because in this case, we have 10 cases of fraud and we didn't catch a single one of them. So this could be a very costly mistake, even though our accuracy looks very high. So this is why we might need additional metrics for evaluating our classification model. And two super important ones that we're going to use are called precision and recall. And together, precision and recall will give us a more complete picture of how well our model is performing. Let's say that these are all of our data points in our testing set, right? These are all of the data points in our testing set. And the red ones are the actual positive data points, and the green ones are the negative data points, right? So far we haven't introduced a model yet. These ones are just positive ones, and these ones are negative ones. Ideally, we want our model to do this. So we're going to represent our model with this red box, right? So in a perfect world, our model is going to predict positive for all of the positive ones, right? For all predicted positive, they're actually positive, right? So everything inside that red box, we want it to be red, right? If there's a green one in that red box, that's not good. And then for all positive, they are predicted as positive. So we don't want red ones outside of the box, right? So the same way we don't want green ones in the box, we don't want red ones outside of the box. In this perfect world, all the red ones are inside the box and nothing else is inside the box. So the first concept we're going to look at is precision. And this is the fraction, in terms of this example, this is the fraction of red. This is the fraction in the red box that is actually red. So we're talking true positives over the total predicted positives, right? So if we look at everything inside of the box here, right, what fraction of it is actually red? Let's take a look at it for maybe like a confusion matrix that looks like this. So for precision, if we're looking for the fraction of the red box that's actually red, that would be like the number of true positives, right? So these are red dots inside of the red box over the total predicted positive. So that's everything inside the box. So if we think of it here, it's like just these red dots over the number of dots inside of the box, right? So let's go back to this example, right? What is the precision here in this same example that we were just looking at for the fraud? If the precision is calculated as the true positives over the true positives plus the false positives.
It'd be 0.
Yeah, awesome. In this case, the precision is 0, right? Because we didn't predict any positive at all. So our red box kind of doesn't even exist, right? So this is kind of like a little gotcha to this little hack, right? So before this had 99% accuracy, right? But the precision is actually terrible. It's actually as bad as it can get. It didn't catch a single one of the positives, right? So we would say the precision is 0 here. And this is kind of like, this is one metric that we can use, right? To say like, oh, this kind of model that we created, even though it's accurate, it has some flaws, right? And this is one of the flaws. It has really bad precision. When we're thinking about precision, one more time, if we're using a confusion matrix for 2 classes, it'll be the true positives, this square, right, over the total of these 2 squares combined. So in this case, it was 0 over 0, right, because we never predicted positive. So the next concept that we want to discuss is recall. And recall is also going to be important. So for all the positives, we want to make sure they're predicted as positive. So we're talking about for the fraction of red dots that are in the box. This is the true positives. So we're going to do all the red dots that are in the box divided by the total number of red dots, right? The more red dots we have outside of this box, our recall is going to go down, right? If we look at it like this, recall is going to be the true positive over the total positive. So it's going to be this box, right, the true positive, divided by the sum of these 2 boxes. So if we come back to this fraud example, what is the recall here?
It's still 0.
Yeah, it's still 0, right? Because we're doing this box, which is 0, divided by the sum of these 2 boxes, which is 10. 0 divided by 10 would be 0. And this makes sense too, right? Because if we talk about the fraction of dots that are inside of the red box, we do have like 10 red dots, right? But none of them are inside of the box, right? So our recall would be 0. So here's a question. Which metric would we most care about for optimizing our fraudulent transaction detector? So would precision be more important or would recall be more important? Keeping in mind that false positives, like the normal transactions that are flagged as possible fraud, are more acceptable than false negatives, where fraudulent transactions that are not detected. Yes, the correct answer in this case would be recall. And let's talk about why that would be. Let's kind of switch the numbers around and do a few more hypothetical situations, right? So let's say this is what we have here, right, with fraudulent cases. So maybe now we have still 10 fraudulent cases, but we are correctly predicting all of them as fraud, right? But maybe now we are also having a lot of, we're having like a lot of false positives, right? In this case, the precision would be 10%, right? Because if we were to do the 10 divided by 100, we would get 10%, right? But for the recall, we would have 100% recall because 10 divided by 10 is 1 or 100%. Here in this example, our incorrect predictions may slightly inconvenience people, right? So we have maybe 90 people who might get their credit card frozen because we are suspecting fraud, right? So these people might be slightly inconvenienced. But let's look on the flip side of the coin, right? Maybe we have a confusion matrix that looks like this, where in this case, we have a really high precision, but lower recall, right? So maybe we have 100% precision and maybe 50% recall, right? So half of the fraudulent cases we are detecting as fraud, but the other half we're missing, right? In doing so, we never suspect fraud when it's not fraud, right? So in this case, we have high precision and an okay recall. But here, our incorrect predictions may have big consequences, right? So if we have these 5 cases of fraud that we're missing, right, and we're letting slide under the radar, this could have huge consequences for the owners of those like bank accounts, right? They could become like victims of fraud and like lose a lot of money. So this is something we would want to avoid in this particular situation. So in this case, if we have these 2 matrices, the better one is actually this one over here, right? So even though this one on the right side has better accuracy, right? So we're making fewer mistakes, right? In this one, we only made 5%, but in this one, we made 5 mistakes. In this one, we made 90 mistakes. This one is still better in this case because when we're doing a fraud detector, right, we want higher recall. But there will be other things that we might detect. So like if you're detecting like spam emails, you might want higher precision. Or if you're doing like a object detection image classifier, like we're doing, you might want to consider both precision and recall. So the type of metric that is most important will really depend on your business goals. In summary, today we talked about 3 classification metrics. We talked about accuracy, which is like the fraction classified correctly. We talked about precision, which is the fraction of things we classified as positive that are actually positive, right? So the true positives over all of the things we predicted positive. And we also talked about recall, and this is the fraction of positives picked up by the model. So this would be the true positives over the total number of positives. Some other important takeaways of today. First of all, the confusion matrix is awesome. It's going to give you a more complete picture of how your model is performing. Both visually, it's helpful for someone who's trying to get a sense of how well your model is doing, but also quantitatively, it'll help us compute various classification metrics like our precision and our recall and things like that. And finally, the best metrics to focus on will depend on the business objective of your project. Today, we talked about how we split our data into different sets, training, testing, and sometimes validation, and then how we could evaluate the data inside of our test set. That might involve producing a confusion matrix and then calculating metrics like accuracy, precision, and recall. There's other metrics as well beyond just those 3. There's actually many, many different kinds of metrics that you can use depending on your project. These 3 are really like common, like popular ones that really will paint a pretty good picture for you of how well your model is doing. That concludes our lesson today on evaluating your classification model.